Spacetime diagrams is the subject of this video, and they are different from the diagrams that I've been drawing this whole time. Yeah, and so they make a really useful tool once you figure out how to use them. So what you're used to, or what I've been describing all along here, are just essentially drawings of X and Y coordinate systems. And if this is an observer frame, I keep saying that there is a clock everywhere, a separate clock. They're all clocks belonging to this observer frame. And all these clocks, they maintain their relative locations within this space diagram. And I'm making somewhat of a joke, but it's a space diagrams because it's a picture of the X, Y, and Z directions. Z is the third axis that I'm not drawing explicitly, but it's understood. It's here. And there are an array of clocks throughout this three-dimensional space diagram. A space-time diagram is a different kind of diagram, though. A space-time diagram actually puts as the axes a space axis and a time axis. Here is an example of a space-time diagram that typically gets drawn. It looks like this. Time is put on the vertical axis, and space is put on the horizontal axis. This is the space-time diagram, and you can have negative values of time and negative values of position too in the x direction, right? What's more is like it really could be, yes, so this is the space-time diagram. In earlier classes, you would have done a different kind of diagram. It's got the position and the time swapped. In earlier classes, you may have seen graphs that look more like this. So as a function of time, so time is like the independent axis, there's x of t, and you can have some sort of like trajectory or something. And so the way you read this is at this time, there is a position x1, and at this later time, there is this other position x2, and you could do things like the average velocity between time 1 and time 2 is x2 minus x1 divided by t2 minus t1, right? So this is some stuff from earlier. And space-time diagrams in relativity are actually related, but it's kind of like you took the axes, like time and space, and you are turning them to look at them in this picture here. So this is now time, and this is space, right? So x and x is the idea. So it's just a different tool, but this is a really useful way to keep track of events in special relativity. You could do special relativity on these kinds of axes, but this is what I'm going to show you today, a space-time diagram. So remember that Lorentz transforms tell you how to relate event data. This is Lorentz event transforms in particular. So they relate event data between two reference frames. And so what I mean to show you is, so if I have, for example, an event. So an event in a space-time picture is a point. Right? Event is a point. And we could say that these are the coordinates that belong to O's frame of reference. And there's an event, and we could call this event E. And so this event recorded by observer O has space-time coordinate, say t comma x. And actually it's funny, like, yeah, so, unfortunately, you know, when, it's kind of like, the horizontal axis in mathematics is often the independent variable, and then the vertical axis is the dependent variable. And then you tend to put the horizontal axis first in the coordinate and the dependent variable second in the coordinate. That's how you tend to learn it in your math classes, and that's how people tend to draw it. But in relativity in physics, people tend to mark the time coordinate first and then the space coordinates afterwards. I guess it's just a, yeah, it sort of doesn't matter. But I'll put it this way. And then, for example, O prime, right, has a different coordinate system, x prime, t prime, but this event right here also happens, right? The event happens regardless of who sees it happen. So I have two different observers that happen to have a relative motion between them. But they still can record the same event with all their detectors. And observer O prime is going to record the very same event E, but with different event coordinates. So has coordinates t prime, x prime. And if O prime and O have relative motion u, so O prime moves to the positive x at speed u relative to O. And so immediately you can write down that t prime is equal to gamma of u, and this is, yeah, I'm basically copying from my post-it note that you may have seen in the videos before. So t prime is gamma of u, t minus u over c squared x, and x prime is equal to gamma of u x minus ut. So this is the translation of event data recorded by O to event data, same event, event data recorded by O prime. So the next thing to do with space-time diagrams is to talk about things moving with a space-time diagram. So, for example, here, so maybe the typical starting point is, let's look at light. So a light signal, or actually, let's make it a flash. A light flash happens at, say, t comma x. So this is so t comma x equal to 0 comma 0 in O, right? So this is an event, right? So this event happens at 0, 0. So let me draw a space-time diagram. So space on the horizontal, time here, and 0, 0 is right there at the origin, right? So there's the event. But when a light flash goes off, right, it goes off here. What it's going to do is actually travel both in the positive x direction, but also in the minus x direction. But you know that as it travels outwards, it has to do that it has to do that while the clock ticks forward in time. So the light that heads out the positive x-axis on the space-time diagram is going to, along its trajectory on the space-time diagram is kind of in a diagonal line, and the negative direction is the same, like this, right? So, but you know that space and time are going to be related by the speed of light. So in particular, we're talking about light traveling as one possible thing that moves in the space-time diagram. So light travels at speed c, and that's the speed it travels in O, right? And actually, it'll be the speed c in every inertial reference frame, right? All the possible inertial reference frames. That's the quirk of the second postulate of special relativity due to Einstein. But anyways, what this means is, it's interesting. So travels 1. So this is an interesting unit. So it travels 1 light year per 1 year, right? So 1 light year is equal to c times 1 year, right? So c is a speed, it's a distance per time, and if I multiply by time, I get a distance. So the light year is a distance unit, right? And this is, you could say, is the definition of the light year, right? So this is a nice thing. So 1 light year per year, and if I was to think of the x-axis in the units of light years and the time axis in units of years, then traveling at 1 light year per year makes it so the light, by the time it gets to, right, 1 light year, it took 1 year to do that in. And to get half of a light year in distance, it takes half a year, right? And a third, and etc. So what this does is it puts us a line that represents light traveling in the positive x-axis as time goes into the future. And likewise, the light is going to travel 1 light year per year also in the negative x direction. So it goes like this, right? And so these lines have a special name. They are called world lines, right? So this is the world line. A world line marks the set of event, and I'll put in parentheses points, that represent the, say, existence of a, for example, particle, but I'm going to put a thing, right? And so a world line, this is a nice concept to have. It's a drawing of all of the lifetime event points of a thing that exists during time. So that's a weird thing, but it is a set of events, right? A set of points, right? A line is an infinite set of points. A curve also is an infinite set of points. So these world lines, yeah, they're marked off for speed of light, for things that travel at the speed of light. Yeah, it travels 1 light year as 1 year goes by. Okay, so things, though, that are other than light, and it turns out massive things in particular travel at speeds slower than c, right? So as an example, let's give a velocity to a thing that's a massive thing equal to half of c. And what this means, I'm going to describe it. It travels 1/2 of a light year per 1 year. And so, for example, let's draw a space-time diagram, and I'm going to draw it kind of funny. I'm going to say here's the x-axis, and here's the future time axis, and this is the past. And in the past, there is a thing that leaves at, say, 2 years before the origin of time, right? So the origin is kind of arbitrary. You can imagine existences before the time t equal to 0 mark, right? So at -2 years ago, but at 1 light year in the positive x direction, this marks the first time that we keep track of an object that moves at, I'm going to put negative half of c. So it moves, say, a negative displacement, a displacement towards the left of half a light year per 1 year. And so what that looks like is this is the world line of it. So if you wait, or if observer O waits 2 years, then this object will move from here to the origin, right? And if it keeps this speed for a little bit of time, it'll go into the negative values of x. But let's say that at some point, this is kind of a cool thing. So let me extend the space axis back. And let's say that at the 1 year time, the object is, for some physical reason, made to stop. So if it stops when it gets, so let's see, so 1 year later, it would only travel to -1/2 light years, right? And if it's made to stop, then what it's going to do is just its location on the x-axis is no longer going to vary as you wonder what happens to it into the future of 1 year, right? So this is a world line associated with something at rest, and this is a world line associated with something with a velocity equal to -1/2 c. And this right here is an event. You could say that this is the creation of the thing, right? And it's sort of unphysical, but you might mark this corner as an event also, where this event is an abrupt change in motion. It's like a crazy deceleration, right? Like all of the motion is lost at that event, which requires an infinite force and stuff like that. But yeah, so these world lines are sets of events that mark the existence of an object. It's actually the location of the object as you think about time going into the future. So the next thing, let's think about extended objects in space-time diagrams. So for this one, this is kind of cool. Let's imagine that there is a reference frame. So here is x, t, except for I'm going to call this O prime. And I'm going to say that there is an object in O prime that stands still. But this object is extended. It's extended in the x prime direction. So I'm going to say that this is the object's left-hand coordinate, and actually I'll put lowercase l, and this is the object's right side end. And if the object is at rest in O prime, then the left-hand end doesn't move to the right or the left, and the right-hand end doesn't move to the right or the left, right, as time goes into the future. So this is world lines of left and right ends of a stick. And the length of the stick is equal to, let's say that the right side end is the bigger value in x, minus xl prime. And because this is the rest frame of the stick, right? We know it's the rest frame because the left end and the right end are not translating as time goes into the future, right? The left and the right ends have constant values of x for all the values of t. So because this is the rest frame of the stick, L is the proper length. And I'm going to doctor this up. I'm going to say this right here deserves a special marking. So the sub naught, yeah, so L naught is this proper length. Let's say that O prime moves to the right at speed u in O, right? So this is a speed u. So this is the relative frame motion. So that means that if O prime moves to the right at speed u in O, and the stick is at rest in O prime, that means that this stick moves to the right inside of O. So let me draw. Notice that this is x, that's x prime, so they're different. And this is t, and that's t prime. They're different. This is the observer O. And there is a moment in time where the stick has location x sub l, not x sub l prime, and this is x sub r, not x sub r prime, but the left end moves to the right at speed u. So this is the world line of the left end of the stick. And this right here, this parallel line, is the world line of the right end of the stick. So these are world lines of left and right ends of a moving stick. And xr minus xl is equal to L as measured by O. But let me note really carefully. So these XR and XL are changing in time, right? So carefully, O must measure XR and XL separately at the same time in O. I alluded to this problem very early on about talking about measuring the length of something that's moving. You have to be very careful, right? Even in classical relativity, that your XR and your XL are measured at the same time, or at least with that issue in mind, because you could probably back calculate and figure out what the length is, even if you were only able to measure one end at a time or whatever. But this is kind of the point. The reason why this is important is because there is a relativity of simultaneity, right? So this is the caution, cuidado.